and graphs of exponential functions again. So what we want to recognize here is that there are multiple ways to write the same exponential function. And we're going to take a look at how we can do that using exponent laws. So if we take a look at y equals 25 to the power of x, we can change that base. Now we can't change the number itself, but we can change how that number is written. So we know that 25 can be written as 5 to the power of 2. So inside here, we can write 5 squared to the power of x. Now we can simplify that. We know exponent laws tell us we're just simply going to multiply our exponents on a single base, which means that that function can also be written as y equals 5 to the power of 2x. So we still have that 5 squared from our base of 25. So yes, we've changed the base, but just basically how it's written. We could also use this to rewrite 25 as a negative exponent. So what we could do as well is write 5 squared, which we know is here, as 1/5 to the power of -2. Remember, 1 over 5 to the -2 is still 25. And this would also be to the power of x. So we could also rewrite this function as y equals 1 over 5 to the power of -2x. And because remember, we know that a graph of y equals 2 to the power of x is a reflection around the y-axis of y equals 1 over 2 to the power of x. That simply means that where our function was increasing changes to decreasing and vice versa. Okay, so it makes sense that these two would be the same graph with a negative exponent, because we would have a reflection to the 1/5, but a reflection back with the negative in front of the exponent. For our second one, again, wanting to rewrite this, we know that we can rewrite this using exponent laws a couple of ways. We know that 4 to the 1/2, we can separate what is multiplied out here to individual powers. So we know that exponent laws tell us that if we have 2 powers on a single base, we multiply. Well, we can also put brackets in there and divide those exponents. Now, inside here, we know that 4 to the power of 1/2 is the same thing as square rooting. Remember, we talked about the bottom of the fraction for the exponent comes around to become the root. So inside here would become 2, and then we can simplify to 2 to the power of x. So, and again, thinking about why that makes sense graphically, that if we have a graph of y equals 2 to the power of x, and we have y equals 4 to the 1/2 x as our exponent, the graph would be twice as wide for this one, which would map it onto our graph of y equals 2 to the power of x. And if you want to take a look at those graphs, graph those two graphs on decimals, and you can take a look at why that makes sense as well. Now, the other way that we can rewrite this one up here as well is making the 4 a fraction, right? So flipping that base of 4 to the bottom just makes our exponent a negative. So we would have y equals 1/4 to the power of -1/2 x. And again, graph that using decimals and take a look at our properties so that we can compare those as well. For part C, we have a base of 6 here with a 36 out front. First thing we want to recognize is that we can write 36 with the same base of 6. So 6 squared times 6 to the power of x, we now have a common base, which means that we can add our exponents. So we're going to have 6 to the power of x plus 2. Well, in part D, we can do the opposite. So since we have x and negative 3 added, remember we can think about minus 3 as plus negative 3, that means that we can separate those two parts of our exponent. So we're going to have 2 to the power of x times 2 to the power of negative 3, each having its own base. So the opposite of what we did over here, we added our exponents. Well, now we're going to separate what was added into their own exponent. Well, now we know that this part here we can simplify because it's just a value. So we're going to have 2 to the power of x, and we're going to flip this to 1 over 2 to the positive 3. And now we can simplify. 1 over 2 to the power of 3 is just 1/8. So we're going to put our number out front, and we're going to have multiplied by 2 to the power of x. So we can see that there are different ways to represent the same graph using exponent laws. Now, taking a look at graphically what this means. So example number 2, we want to write two functions from this graph. Well, we notice that we have an asymptote at y equals 5, which tells us that graph has been shifted up 5 units. So we know we're going to have a plus 5 at the end of the function. We also recognize that our exponential function goes down. So we have a reflection in the x-axis, which means we have a negative y. Our y values have changed from negatives to positives and vice versa. Now, what we want to determine is what is our base. We do recognize that where we normally have our y-intercept 1 away from the asymptote, which is normally down here and up 1. Well, from our asymptote here, it is down 1, so there's no stretch or compression or anything like that. So what we look for is 1 over. What to the power of 1 gives us this point? Well, it's 2 away from the asymptote, which means that our base has to be 2. And we can double check that. If we had 2 and 4 away from the asymptote, or down from what would have been the x-axis, then we do know for sure we have a base of 2. So we know we have a base of 2, it's been reflected and shifted up 5 units. That means that we can write this as y equals, remember if we have a reflection, our negative goes out front to change the whole thing, times 2 to the power of x, which is our base graph, and we have plus 5 at the end. And we can double check going from what equation we have to make sure that our graph makes sense. Our asymptote plus 5, our base function of 2. So if we want to think about what points would have changed from our graph here, we have reflected around the y-axis and moved up 4 units. Reflected around the y-axis, moved up 4 units. So we do have our graph. Now we just want to show this 2 ways. So we're also going to flip our 1/2 in the inside, and we're going to write that exponent as a negative x. Again, that just simply flips our fraction. We know that a negative exponent means we're just going to flip, so we can do that either way. Okay, so we have our two representations of that same